Here we are, live. It's Saturday morning tonic and we're doing live session number 9. Some of you may be confused. I put out that we're going to be on at 10 a.m. in UK time and it's 11. And that's due to time differences. It's the strangest thing. We have a time difference and a couple of weeks later it changes again. So it'll settle down after next week, I'm sure. Now, so this week we're looking at indices, standard form, reciprocals, rational numbers and surds. It's a big topic. It's an important topic if you're doing higher paper. There are 40 days to go, 40 only. And to put that in more perspective, next week there'll be 33. It's really counting down. We're down to a third of where we started these weekly sessions, and that's how quickly it can go. But have a look at what regular practice can do. We're already through 10 subjects, and that's not 10 minor topics, it's 10 entire chapters of a book. So, doing well. And once again, if you want these questions before the session, go to Patreon. They are there for free. You don't need to sign up or anything, just grab them and stick around after this. In fact, no, this week will be slightly different. Tomorrow I will be finishing the next questions and uploading them. So tomorrow, give yourself a night off from downloading them and starting them really early, and give me some time to finish them. There's some good ones coming. They're very tricky, I would say, but it's going to be on proportion, direct and inverse. So some really tough and good stuff. All right, should we get started on this week's? So this week's begins with evaluating the following. Well, you know, some of this stuff is just so basic, but it's got to be said. It's got to be done, because year on year, it still gives people trouble. Okay, ready to start. 34 to the power of 0. Some ridiculous number like 34, because nobody knows that 34 squared, because it doesn't matter. Anything to the power of 0 is 1. And there's a number of ways of proving that, but not what we're here to do. When you're doing GCSE Higher, this is one of those that you need to know straight away. Right, B. What do we think here? I did another ridiculous number to really see if you know what you're talking about here. So obviously nobody wants to write -1 times -1 11 times, but it's probably worth doing it 5 times just to see what happens. So as we can see here, where there's 2 negatives, it becomes a positive because we've got 2 negatives, and well, that's fairly straightforward to see. If we have 3 multiplications, that's a positive overall, but then that's a positive times a negative. So it becomes -1. So the 1 doesn't change, but this one's going to be negative. If we think about this in terms of indices now, this is -1 squared. This is -1 cubed. What we're going to find is that all of the evens are going to give us a +1, and all of the odds are going to give us a -1. So 11 being odd, I think we might just move this to the side, like so. 11 being odd, we know that the top is actually -1 over 3. There we go. Interesting concept, actually, just really inflated there to make a point. Look at that question. Hits you hard, eh? Let's have a look. 3/4 x to the -6 in fraction form. This is currently index form because we hopefully realize that this negative index implies reciprocal. In other words, 1 over. And there's a couple of ways we can look at this. Let's get started with one way. 3/4 times x to the -6. There is a secret multiply sign, and that means we can separate these two. By adding the multiply, we are adding something called structure. And the structure is kind of showing us the operations. And I use brackets to keep it even clearer. A lot of maths we don't write stuff as a shortcut, but having the multiply there really helps us. And I'm going to keep that structure moving forward so that everything stays clean and we know what is interacting with what. I'm going to sort out the index here. So we're going to have a -6 index. There's a whole thing around this, but I'll probably just I'm going to do it in a couple of ways. Okay, so the real proof way I would say is that x to the -6 is x to the -1 times 6. And where you have a multiply, that comes from the index law of the brackets. And so we can write this as x to the -1. Oh, a couple of anomalies there. X to the -1. Maybe it's the mouse. Let me move that out of the way. And instead of the multiply, we can add the brackets. Now you can probably see, if you were given this question here, you could work backwards to here. And you'd know, oh, the brackets mean I'm going to multiply the indices. What we're going to do is sort of undo that and work backwards and say, well, I'm going to split this into multiplication and add the brackets. And therefore, I mean, we could have done it the other way around as well, like this. Oops, didn't write. We could have had it this way around, and it would have looked something like x to the 6 minus 1. We can just switch this around because when you multiply, it's commutative. It doesn't matter which way around you do it. So in that sense, we've got a couple of options. They're neither are wrong. I actually like the second one more, so we're going to go with the second one. But this is the concept that I'd like to get across to you, that multiplying turns into these brackets. Where does this leave us? Well, now we're pretty free to understand what it means. If anything's the power of -1, it means 1 over. It's reciprocal. And just for fun, we'll have a quick look at how that works. 3 to, let's do squared first, is 3 times 3, which is 9. 3 to the 1 is 3, which is just 3, right? So 3 to the 0 is, we know that's 1, but there's other ways we know why it's 1. We can prove it here. So what's happening as we go down here? We're dividing by 3 each time. So this is the pattern. This is what's happening. So if we want to think about what happens in the next row, which is we're going to take away 1 again from the index, it's -1. What's happening? If we follow the same pattern of divide by 3, it's going to be 1 divided by 3, which is 1/3. And what you're going to see is that, how do we really look at this? Actually, it's better with it squared, so we'll do one more. So let's say we'll take off another one, so 3 to the -2. What does that look like? Well, if we divide by 3, and I appreciate that is even a concept unto itself. Dividing by 3 is the same as multiplying by its reciprocal. So if we do 1/3 times 1/3, we get 1 over 9. But we know that 9 is 3 squared, so it's like 3 times 3. And now it becomes very clear how to convert or understand what this looks like in fraction form. You can see this negative index here, the negative part, seems to imply, so if you've got -1, it seems to imply 1 over. And what is the denominator? Denominator is everything that is left other than the -1. So you've got the 3 there. If you want to be absolutely precise, I suppose we could say that this was 3 to the 1 times -1, which is 3 to the 1 to the -1, and that this -1 means 1 over 3 to the 1. But I'm not going to leave that on there. That's just being thorough and exploring structure. And really, when I've never been taught something or I've never seen an example, I resort to structure, just like I just did then. I think, well, what are the fundamentals of what I know about the structure of this problem? And I just work it through using minor changes and exchanges of expressions till I get to a different sort of truth and I see an insight. Let's look at this amazing thing and how it translates to the second one. Now we want green. So again here, we could write this as 3, no, give me blue. We could write this as 3 to the minus 1. In fact, let's do it the other way around. 3 squared times minus 1. You can appreciate that minus 2 could be written as 2 times minus 1. And as we know from earlier, this times can be written, exchanged with brackets. Right? So now we can see, we know the effect of the minus 1. We saw it here. Anomaly. We saw it here. We know that it's 1 over, so that would be 1 over whatever the brackets, which is what we see over here. Now there's a quick way of looking at that if you're going to just be doing a question like as a shorthand. And that's to see that we know the presence of this negative means -1 is multiplying the index. So that negative means the 1 over. And then the 2 and the 3 are what's left, and they go on the bottom. So let's just test that out quickly with another one. 3 to the minus 4. I'll do it properly. So we have the negative, which means 1 over. And then what is left is 3 to the 4. And that would be correct. So that's the way we're going to play this. So look at that whole backstory. If you've never seen it before, it's kind of interesting to see this little investigation. It's a solid investigation. It can really help. So now where are we? We're at this one. Our question is x to the 6 to the minus 1. And we've explored the fact that -1 as an index means 1 over. I want to move this. I do want to keep it here. Where could I just store this? Maybe I can store it at the bottom of the page. So I'm going to have to walk it down. Oh, no, that's not good. I have to walk it down the page, you know. Wow, that's really well thought out, isn't it? As a program. Every time you move. I mean, maybe it helps. It doesn't help right now, but it might help some other time. Slow, hey? Right, that'll do. That's probably out of the way now. Let's continue with our problem. So yeah, we're thinking about this -1, and we know that's 1 over. That's what it means. Whatever's left, which is x to the 6. So that's what's going in there, is 1 over x to the 6. Gosh, I'm hoping some people found that explanation useful, but we can have skipped to this point if you haven't already. And I will leave that. Yeah, I think we'll be able to fit this in if I just move this across a bit. And now we can see that we have fractions. We've got one fraction multiplied by another, and it's a simple case of multiplying the numerators and the denominators separately. Now, you wouldn't believe the people that I've taught that get to the GCSE and have never seen how to multiply fractions, although I will say that I believe that it is the first step in your journey to GCSE. You need to master fractions, and you need to not have to think about how to deal with them. They ought to be something you practice frequently. And that's a good tip, especially this late. There's no time like the present to start. So we've got a final answer, and maybe there's some simplifying to do. No, there isn't, but there could have been. Our final answer is this. I mean, technically it is there as well. Okay, simplify. I guess here there's a couple of approaches, but I'm not seeing anything too obvious. The first thing we need to realize is that everything on this top is a factor. What does that mean? It's multiplying. It can be separated out as something that's multiplying everything else. So if I took this 8, I could move it around, I could tick it out the front, and it's multiplying everything else. It's a factor on the top. And any factor that's on the numerator can be cancelled with a factor on the bottom. So I can initially cancel out some of these if I want. I can cancel out those. I can cancel out y with this y. I'm just pick out single ones. Is there an x squared up there? No. So I can cancel this x squared with this 3, and then it's just x to the 1. So there's a couple of things I could do there. First of all, 3 times 3, 9, 8, 7. It's not really going to work any better than just this. So let's write out what damage has been done so far. So it's 3xz times 3xy squared times 8z cubed on the top. And on the bottom, just 10. So that's really kind of useful. The more simple an expression is in the exam, the more you're going to benefit. And we're just going to simplify the top now, so the numbers are going to go first. So we've got the 3, 3 and the 8. Dun, dun, da, da, da. Yeah, so that's 9 times 8, which is 72. And then x, that's x squared. And then z, we've got a few of z, so it's going to be this z multiplied by z cubed, so it's z to the 4. And ordinarily I'd tick it as I go along, but I probably should have done the y's first, but it doesn't matter too much. All over 10. And we can go a little bit more simplified because the fraction's 72 over 10. Now when we talked about structure, we could separate this and write it in a different form so that technically this is the equivalent, because any number would multiply the numerator, and so you can see that by performing this multiplication we would have this, and so therefore it's equivalent. That leaves us free to see that, okay, that's done, but this fraction is something we can isolate and focus on, because when it's mixed up in this bunch it's a little bit difficult to see. So we know that 7.2 is the answer here, but that's not, we want whole numbers really, so we're looking for factors, and if we just do the prime factors of 10, we're talking 2 and 5. So we really only have the option of dividing by 2. So 36 over 5, how do I want to write that? I'm going to write it like 36 x squared y squared z to the 4 all over 5. By the way, that whole prime factor thing, like, what are you doing? That's so extra. Kind of, but when you look at how to cancel fractions and, well, a lot of really advanced stuff with factors, prime factors are absolutely brilliant. They are so revealing and useful, and I recommend using them in a number of situations of division. Right, last one. Here's the last one. This is putting everything together and introducing a new thing. What happens with indices and fractions? So yeah, let's get my highlighter out. We've got 3 elements here on the index. So this is the subject, this is the base, and this index is going to happen to it. There's 3 things going on here, and we'll break it down with structure so that you can hopefully see what's keyed in. Now you probably note that these are cube numbers, so there's something to do with a cube root would be real good. Now this number here can be written in as a multiplication of 3 things. Remember that trick that we did earlier where we said every one of the multiplications, actually want to accurately hit that times, can be replaced with a bracket. And further, we said that these can be written in any order. So yeah, they can, because they're being multiplied. The question is, when we add the brackets, do we want to add them straight like this? And therefore do the reciprocal first, then square it, then cube root it? Because, by the way, the power of a third, you should know, is a cube root. That's quite an important fact. Just like if I had the power of a half, we know that it equals the square root. Try and remember that. So that might not be the best order, right? I think that it would be nice to do the cube root first, because this makes numbers smaller. And therefore, if I write this, remember, this is the way to do it with structure. I'm going to come back at you in a second with the quick way of doing it. It's kind of similar way, but how you can interpret the fraction quickly. I'm probably going to cube root it first. I'm then going to square it, why not? And then I'm going to reciprocal, because that's the easy one. Like, it doesn't matter when the reciprocal occurs, but okay, so there are 3 brackets here, and these are what we call nested brackets, and we start from the very inside bracket and work out. So the effect of the inside bracket is the third, and it's going to act upon what's inside. Now, with a fraction, indices apply to both, just like they apply to both when there are 2 elements multiplying each other in a bracket. They apply to both separately. So to write that out at the side quickly to show you, that's 125 to the third and 216 to the third. And that's what it looks like. And obviously we're going to do it so it's separately anyway. Probably jump straight to it. That the third root of 125 is 5 and the third root of 216 is 6. So that gets that inside bracket out the way. And we still have the squared, we still have the reciprocal. But we can deal with that one at a time. Oh, anomaly. How many times do I say that every session? I don't know. Squared is now going to apply to 5 and the 6. So if you didn't know that rule before, you've just had 2 practices in one question. Not bad. And therefore this becomes 25 over 36. And the reciprocal is still to be dealt with. But the fantastic thing about the reciprocal is that it just flips the fraction upside down. So it just does that. There's the answer right there. Okay. I suppose there's one more thing to look at here, because I guess I'm jumping the gun a bit, like what reciprocal is. The definition of reciprocal is if I take any number, let's say 3, the reciprocal is the thing that I multiply that by to give me 1. So hopefully you could tell me that that was a third. And if you start doing enough of these, you start realize that, oh look, it's always the same thing. It's like 1 over whatever that number is. Wonder why. Okay, what if it's 2/3? What if it's a fraction? What do you multiply it by to get 1? Well, it would be nice if there was a 3 on top to cancel the 1 on the bottom, and a 2 on the bottom to cancel the 2 on the... Oh, okay, that's weird. It's just flipped upside down. And that's true as it comes. How does that apply? How do we find a general rule, or do we have to remember differently for fractions and numbers? In fact, there is a general. If you think of 3 as 3 over 1, I think we can all agree that 3 can be written as 3 divided by 1. Remember, find those equivalent expressions to reveal new truths. 3 over 1, oh, it just flipped it upside down, so it's 1 over 3. Same with 5. If you think about it, it's 5 over 1. So I think the trick is, I suppose you can remember that whole numbers just become 1 over. But technically, you're flipping the fraction. Okay? So that's why I flip the fraction if I'm trying to find the reciprocal. Because that is the number that to get to 1 when multiplied. Similar principle is used in gradients All right. We're done. Question, page one. Page one. There's quite a few skills here. So that was indices, I suppose, largely. There's still some indices here, but now these are standard form. If you probably picked up on a number between 1 and 10 multiplied by a power of 10. And they're designed so that you don't need to use a calculator. But there's a few decimals here, so it depends what paper they put it on. Like, it could be on any... It was a time where it was only found on the non-calculator, but you never know. So the mass of Neptune is very small, not. This is way more indicative of the size. There's like 10 zeros to be added on here, or 10 decimal places. And although this is looking bigger, 6.4, it's definitely not, because it's the power of 10. This is an order of 1,000 times bigger, right? So there's 3 extra zeros or decimal places. So it's very much larger Neptune, and we probably knew that anyway. So how many times heavier is Neptune compared to Mars? Give your answer in standard form to a suitable degree of accuracy. Yeah, so how many times? Hopefully you thought it was a division. So we know Neptune is actually bigger than Mars. So we're saying how many times does Mars fit into Neptune? And that's a division, isn't it? How many times something goes in. So Neptune is 1.03 times 10 to the 26 all over 6.4 times 10 to the 23. This is where the beauty of the standard form comes about, because if I wrote this number out fully, it's a very big number to deal with. But if I compartmentalize it into 2 factors, these 10 as power can be cancelled down real easy. So we have 10 to the power of 3, because you're going to do 26 minus 23, because they are the same base. It's index law there. And the number over here, so we're looking at 1.03 divided by 6.4, which is 0.1609. Let's move that and do the whole thing just to show you what my calculator says. Now the question we ask ourselves when finishing this is that in standard form? Look, it says you have to put it in standard form. And the answer is no, because this number here needs to be between 1 and 10. So we're going to give that a bump up and say it's 1.6. And I really feel that that's a suitable amount of accuracy, because if this is 0 next, it's a nice place to stop. It asks me for suitability, and let's be honest, you can't go wrong. They're not going to mark you down for doing 3. Maybe they would for 4. But 1, 2, or 3, it's fine. And I'm going to make my life easier by doing this. So if this is made 10 times bigger, like this number is a number in itself. So it's 1, 2, 3. So it's 160.9, right? This is the number in full. And if I made this first part 1.6 and kept the second part the same, the number is it's like 10 times bigger than it should be. Can you see why? Hopefully you could see it's because you can't just change a part of the number and expect it to stay the same. It's not truth. You can't go around doing that as much as we want to do it. We have to balance. And I call this the balancing method. It's fairly straightforward. If I make one of these parts, remember there's 2 parts here, 2 factors. If I make one of them 10 times bigger, I have to make the other one 10 times smaller in order to balance that back out. So how do I make 10 cubed 10 times smaller? Well, 10 cubed is 10 times 10 times 10. Sorry if I'm teaching you to suck eggs here, but to be honest, some people might just need this. 10 times 10 times 10. I'm going to make it 10 times smaller. It's 10 squared. So I take away 1 on the power. And we want to write that we rounded that to 1 decimal place, because it asks us for a suitable degree of accuracy in the question. And there you have it. Quite easy. What sort of accuracy have we lost? Well, 1.6 times 10 squared is 1, 2, it's 160. So rather than 160.9375, it's 160. It's okay, it's good enough. And it's 160 times bigger. Looking at the size of those original numbers, would you have thought it was 160? Maybe. Maybe. We knew it was a magnitude of 3. So let's go on to the next one. What would their total mass be? Oh, nice. Yes. So mass is measured in kilograms, so we'll keep kilograms. And this question is brilliant because it's a lot like Surds in the fact that you can't add two standard forms together unless you have the Surd. Well, let's talk about it instead of a standard form, but unless you've got the same power of 10. And with Surds, you have to have the same Surd. So, for example, I can't do root 2 plus root 3. It is not equal to root 5. Okay, it's not. You just can't do this. The only way to do it is to think about it in terms of, let's talk about root 8, and let's do root 32. That should work. Now, these two, they're obviously not the same Surd right now, but if we simplify it, this is 2 root 2's, and 32 is 4 root 2's. Now, I'm not going to get into why right now, but I'm just going to make a point that all of a sudden, this is a certain amount of root 2. It's 6 root 2. And so there's a combination possible so long as there is a factor in common when simplified. And that's very similar to this. This is, at the moment, a certain amount of 10 to the 26 plus a certain amount of 10 to the 23. These 10 to the whatevers are incompatible, but if we can rebalance the question so that they're the same, we can add them together. It wouldn't make any sense to add these because they're not additions of the same unit currently. Which one do you want to do? Do you want to make this one 10 to the 23 or this one 10 to the 26? Hell, let's do both because, you know, maybe you like it a different way and I've got to cover both. If we want to rebalance the first one, this would be 10 to the 23. What have you done? You've made this side 1,000 times smaller, right? So this one has to be 1,000 times bigger. So that's going to be 1, 2, and 3. So just one more. So 1,030 times 10 to the 23 plus 6.4 times 10 to the 23. So well, it's insane. That's a very big number. 1036.4 times 10 to the 23. You see, because we've got a certain amount of 10 to the 23 it's 1030 here and 6.4 here, and that's 1036.4 10 to the 23. Not something I say very often, so it's a bit of a mouthful. I get that. So yeah, that's how we combine it that way, and then we want to turn it back into standard form. Perhaps that's going to be 1, 2, 3. So we're going to reduce that back down. So 1.0364, and if we reduce that down 3 times, it seems to be that putting it into the 10 to the 26 to begin with would go straight into standard form. And as promised, let's go. Actually, let's not get rid of that because somebody might want to see that in the answers. Let's use a different color to do the other way. So if we're now going to rebalance to 10 to the 26, the second number is going to have to reduce because we've increased this number by 1,000. 3 does what it is. So this has to get smaller. So 0.0064. And therefore, this very small number is going to add to this one now. And we will find that it's 1.0364 times 10 to the 26. Now, just to be sure, that previous one also turned into 1.0364 times 10 to the 26 when it was written in standard form. So that's how we do the addition. Super brilliant method there is the balance for adding. get the powers of 10 to be the same. And we finished that page. Good job, everybody. I'm sure you did brilliant. Okay, find the reciprocal. What? Okay, I'll admit this is just a random number, but there is one strange way of doing this. If you have a calculator, just type this number in your calculator if you've got a modern one, and it'll tell you that it's 7/32. So then I'm going to flip it upside down, and I'm done. I was kind of thinking about this. Actually, let's leave that there because may as well. Who cares about the answer? It's about the method. I was going to kind of leave this without calculator. Like I was going to put a no calculator sign. It's fairly easy without one as well, but we're not going to simplify it as easily. So this essentially is tenths, right? And this is 100ths, thousandths, 10,000ths, and 100,000ths, right? Oops. So yeah, this is the fraction before us, written fairly easily as long as we know our column values. And once we cancel this down very slowly, say we divide by 5, that would probably be a really obvious start point. 4375 and 100,000. Oh, it's 100,000. Yep, divided by 5. Well, it must be based on 2 with 1 less 0, etc., etc. Oh, divide by 5 again. That is 875, etc. So you'd work your way down. Eventually, you would get to 7/32, and then you flip it upside down. The reciprocal is just this. So the key here is if you're presented with a decimal, change it to a fraction first. And then we talked about reciprocals earlier. So thankfully, we didn't have to have a lesson right here about reciprocals. And we were ready. Okay, so this number here is a decimal that goes on and on and on. So we have to know what that looks like, really. The dot above the decimal place tells you what is going to be repeated forever. I'm going to call this number here by a name. And that name is X. Okay, this number has a name now because I said so, essentially. And it could be any letter you want, but in maths we tend to be biased towards the letter X. And now we can use, because we've defined it, we can use it in a different way. We can think about, sort of the infinite part of this number. If this number was multiplied by 10, so I had 10 lots of my friendly X, that would make it 9.9999999. I suppose that's why a Dalek sounds the way it does. Repetitive mindlessness. How is this useful? It is very useful because, in fact, we've isolated the infinite part. So I'm going to highlight it with the magic of technology. And these are now separated. In a sense, we've got a decimal part that goes on forever, and then we've got this whole part here at the front. And this is useful for us. If, for example, we were to do 10x and we subtracted x, that would be like doing 9.9999 take away 0.9999999. Can you see what would happen? You've got 9, and then you've got like this fraction part, which is, it kind of goes on forever, so we can call it like this. And they've both got this, so it's 9 plus this fraction part that they both go on to forever. And if you did this bunch, take away this bunch, these two would disappear, and you'd just be left with 9. I mean, hopefully you can see that from the actual question itself, that if we did this takeaway, this 9 here, 9 recurring, would cancel out with all of that. What we'd end up with is, on the left-hand side, 9 x's. On the right-hand side, it would be just 9 take away 0, which is 9. And I guess you have to convince yourself of that. I suppose you could draw a diagram. You could say, let's make it really quick so we don't waste people's time, but let's say there's 9 holes here. And then you had this little 0.9 recurring, like this even. Let's write it like that. And that was in this one bag. And then if you were to take away the 0.9 recurring, like that's literally the bag, take away the little bit in the bag, take it away, what you're left with, just the 9. Anyway, it's dumb drawing, but my attempt. So let's then think about this. How do we get x on its own? Because really it looks like an equation to me. I mean, why would we want x on its own? We've got x. It's up here. It's 0.99999, or is it? Let's divide both sides by 9, and we get x on its own, and come to a very interesting statement. X equals 1. So how is it that x can equal 0.99999, and it also equals 1? Well, it must be true that under this logic, 0.9 recurring is equal to 1. It's something to do with this here, this ... that goes on forever. We humans aren't that good dealing with the infinite, and in fact, this is a major assumption. We will never get to the infinite. So we do assume that it continues in the way that it does infinitely if we're not observing it, if we don't live to see it. But it's something that we struggle with, I suppose. It's a big assumption in maths, and we make a number of these assumptions in calculus. And I think that's why some people are turned off of calculus. They get disenchanted on the assumptions, but can't deny it does work in many settings. Where have we gone to? We've gone a long way round to show that what we asked to do, turn it into a fraction. Well, it can't really turn this into a fraction as such, except if we write that it's 9 over 9, or 1 over 1. So we'll leave it like that. There are some different questions around these type of things that go on forever, and they can get fairly complicated. This is the most interesting one, because we're proving that 0.9 recurring is equal to 1. And sometimes in maths we find the truths that we don't really want to accept intuitively. They say that must be wrong, that doesn't match my understanding of the world. And I've met this multiple times, and all I can say is that sometimes when we trust the methods and the patterns, they reveal truths. But we never want to follow them blindly. All has to go through the lens of human experience. Anyway, there's our answer. We've written this according to the rules of maths as a fraction. As such, I would prefer the number 1. Eek. Didn't mean to do that. But if you want a fraction, there we go. Are we done? We're done the page. Last page, everybody. And it's a corker. The last is the best. Or should I say the hardest? I do hope you don't get this in the exam. But, you know, here it is. I like this sort of question. It's a challenge. Let's forget all these square roots. These are actually surds. What makes it a surd is the fact that when you square root, it's not going to be a whole number. It's going to be an irrational number. And I'll write irrational for a second to focus on. Irrational numbers are numbers that go on forever, just like our 0.99999, except there isn't a pattern. At least 0.9 recurring was predictable, and therefore it can be written as a fraction. But you'll find no matter how hard or how long you try, root 3 will never repeat itself as a pattern, as far as we mortals have ever understood anyway. And so it can't be written as a fraction, let's say a over b. If you move on to study A-level maths, there is a very fun proof that gets, should I say, dare I say, overused, proving that root 3 is irrational. It's fairly straightforward, but it involves assuming that it can be written as a fraction, and you'll soon find something illogical about that line of argument. So it is irrational, and typically these numbers are primes, but they also can be, well, they are anything except square numbers. So if you're going to square root a square number, it's hella nice. If you square a number that isn't square, it's not nice. Sometimes it simplifies to be, let's say, for example, this is not a square number. And earlier we saw that it was root 16 times root 2. This is what I can split it apart like this, yeah? So I can write surds as factors and separate them. And then, okay, this part becomes a whole number. This is called simplifying it. And then this becomes prime number. So eventually they will come down to a fairly small number of simplified. The fact is that they're irrational. And an irrational number, let's say if we multiply it by 2, it's still irrational. If we add 3 to it, it's still irrational. So this is a better way of dealing with irrational numbers, is leaving them like surds, like square root 3. Like square root 3 is way better than all the decimals that go on forever that you'll never be able to see or hold or understand. Somewhat understand anyway. Blab, blab, blab. So I want you to ignore all of that and see two fractions. Yeah, and they're being subtracted. In other words, they are being added together. But, you know, we can call it subtraction. And therefore, we need a common denominator. Oh, I'm pretty sure it's not simple to think about, what do I multiply this one by? Should I multiply it by 3? Will that get me the same denominator as no way, will it? Okay, let's multiply it by root 3. Will that? No, that's 10 root 3. I only want root 3. Okay, let's multiply it by 1/10 root 3. Okay, that's going to give me root 3, but then I got to take away 1, and I can't multiply something and make it an addition. Well, I probably, if I was very careful and then I separated it, it's going to get very complicated. I think the first thing to realize is that we're going to focus on this section. This section is a topic in GCSE called rationalizing the denominator. I put it in here and designed it this way because this is the reason why we rationalize the denominator. We want to work with it. It makes it easier to perform functions, like addition and stuff. So we're going to rationalize this first. And to do that, we find a conjugate. I'm just seeing if there's any other questions, see how much space I've got. I think we're good. And to do that, yeah, we're going to employ a little trick, because you could spend a long time thinking about how you're going to rationalize that. What does rationalize mean? There's a really cool thing. See how much we're learning. See how much gets thrown in here. If I was to rationalize root 3, I've got to multiply it by something that stops it having this irrational side. It would be root 3. If I multiplied it by another irrational number like 6, it doesn't have the same effect. If I multiply it by root 3, magically it becomes 3. This is actually fairly easy to prove with index laws, because we know root is to the power of a half, and so it becomes 3 to the half plus a half, which is 3 to the 1, which is 3. So in essence, whenever you multiply a root by itself, like this, then it becomes a. I'm just thinking of so many different ways that I could do this. This is essentially is root a squared, right? Which is a to the half squared, which is a to the 2 times a half, which is 1. So there's like so many ways. I might leave that there. So how we rationalize something is we stop it becoming irrational. And it's pretty difficult. It's easy when it's root 3. It's difficult when there's 2 elements like this. And I'll tell you why. Because if I multiply this by root 3, sure, I'll get the first part. Because how do I do that? Well, I'm going to multiply both of them, right? It has to multiply everything. And we'll expand the brackets here. Root 3 times root 3 is 3. Woohoo! But then, oh dear, the root 3 is back. Because we're going to multiply a number by that root, and then it's just back again. So it actually is a little bit more complicated. And there's this whole trick around using conjugates. So if we put this in brackets so we can see clearly what's going on, we're going to multiply by root 3 plus 1. It's the same elements, but just instead of a negative, it's a plus. And as we know, when we're multiplying fractions, it has to be the same on the top as it is the bottom. A very, very common error is to think that this has to be a negative, like they have to be different just because the bottom denominators are, but that has to be the same thing. Now this is where people also mess up. They underestimate how hard it is to keep control of expanding a double bracket like this. So I'm going to have to be that person that slows us all down in the interests of truth. And I'm going to use a box method to compartmentalize my 4 multiplications. I just think you end up with less errors that way. He says as he makes an error, no, joke, I didn't make an error, it's good, it's good. Keep copying me. No, don't. You should do it yourself. These diagonals here, root 3 and minus root 3 cancel, and then we've got 3 minus 1, which is 2. Did anyone tell you why you bother doing that? Like, why are we adding these up? It's because whenever you multiply 2 things together, you're essentially finding an area. So this is the width, this is the length, and in here is the area. In a sense, you found 4 areas, but to find the total area, you need to add them all together. And that's why it's an addition. Okay, so this is 2. That's amazing. So let's continue our journey down here. I like to keep structure normally like in a row. So I changed my mind. I'm going to move this instead over to the right. So the bottom becomes 2, which is insanely brilliant. The top is a different story. Should we not write this until we've done both, eh? The top is going to be the same method, but different story, all right? So we've got 2 plus root 3 and root 3 plus 1. Anomaly. Root 3 plus 1. Okay, 2 root 3. Hopefully you're filling these out with me and you did okay. If not, it's going to feel really weird and difficult. And we're going to add them together again. This one unfortunately won't cancel because it's not a conjugate. Okay, it's not a special trick. It's just 2 separate brackets that don't really have much of a relationship. So we're going to add them all together. So we've got 2 root 3 plus 1 root 3, which is 3 root 3, and plus the 2 and a 3, which is 6. And we typically like to write, well, I like to write it this way because then there's no confusion about what goes under the square root. So 6 plus 3 root 3. 6 plus 3 root 3 all over what we found, which is 2. All right, so this is the result of the left-hand side, and essentially we'll confirm now that this is rational. What does rational mean? It's a terminating decimal. I'm pretty sure it is. I mean, it's not really got decimal. It's 0 all the way. So you could at least say that it's not. We know what it's doing. It's 2. If it was a rational, it would still have that square root thing. Now we can talk about combining with the other fraction. So now we're going to bring that in. I'll draw an arrow. It's more like a snake. take away 25 plus 10 root 3 all over 10. Now, job's a good one. We could just multiply this by 10, and then we'll find our common denominator. Now, let's put that in brackets because it's the whole thing that gets multiplied, but there are two elements, so they both need that multiplication affection. Let's do the arrows. 60 plus 30 root 3 all over... wait, why am I multiplying it by 10? Why didn't you say something in the chat? Oh, that's because there's no one here. It's a little joke I like to play with myself. Here, give myself some hearts in the chat. Now, we should multiply instead by 5. I'm getting carried away with seeing the number 10 and writing the number 10. You don't necessarily have to be afflicted with that same issue. Now, times 5 is still going to go in. 15 root 3, subtract 25 plus 10 root 3 all over 10. Bing, bing, bing. We have the same denominator. So that means we're really near the end. 10 is shared, and it's the elements at the top that need to be subtracted. You'll be very careful because these both are subtracted. Left is fine. That can go straight in as is, but we subtract 25 and we subtract 10 root 3. Very common problem, but if you're calm and you've practiced enough, you tend to notice things a bit better. All right, so being very careful here, we've got 15 root 3, take away 10 root 3, that becomes 5 root 3. And then here we've got 30, take away 25, which is 5, all over 10. Now it says simplify, and we wouldn't be doing that. We've evaluated it now, and we're kind of on our way to simplifying. We've got one more thing. We can cancel out a 5 because it's a factor on the top and the bottom. Okay, so the top needs processing a bit. We could take that 5 out, and it becomes root 3 plus 1. And on the bottom, we can take that 5 out because it's 5 times 2. And then the 5s will cancel to give us root 3 plus 1, or in fact, 1 plus root 3. So we're not confused about what goes under the square root. Yeah, I'm sure you weren't. And 2 on the bottom. That's amazing. I find that question beautiful. It looked pretty nasty at first, but it uses a ton of skills, and we've learnt all of this stuff along the way, and a lot of wisdom about using these boxes. Yes, good. If you are looking at that thinking, oh yeah, okay, kind of get that, but you're not 100%, you can ask me for some more questions. I've got so many. So please reach out if you want. Just say question in a comment or something. Or maybe tell me the topic. And I think that was my phone, but it was on loud because I had a alarm set to attend this live stream. Little did I know that I didn't need to be here on time because there wasn't anyone in the chat. But I do tend to get at least some people viewing in the aftermath, and I hope that's really useful. So hello to you. If you do want to stop by sometime or in the comments, tell me what time you would prefer. I'm doing this to suit me, that's all. It's late night for me. It's just gone midnight. And it kind of suits me. It's out of the way. I can have a whole day to myself after a long week. But let me know if a different time would suit you better, and then maybe you can come along and say hi in the live. Would be cool. Currently talking to myself, you know what I mean? Anyway, it's good to help as long as it's, it doesn't matter if it's if there's no one here now, as long as it's going to help someone out there. So if this is you, thank you for coming along, thank you for watching, and well, it's not really about that. You're not here to help me, I'm here to help you. Don't forget to check out the questions. They're going to be released tomorrow because I want to polish up a couple of them. And you can start ahead of next week. And I'll see you next week where we're going to be doing direct and inverse proportion. Looking forward to that one. Anyway, for now, wherever you are, good morning, good evening, and good night.